Okay, we're going to start a new topic, the flow of water through soils. We're done with settlement now. Settlement is a very important topic, and that's why we spent so much time on it. But now we're moving on to water flow. And we're going to use an approach called a flow net to solve these problems. And what we're going to find is that water flow affects the pore pressure. In other words, we aren't going to be able to just use the water table alone to get, what we've been calling U water table. Now we're going to have to use our flow net to get the pore pressure at various locations in our system. The equation that governs the behavior of water flow is the Laplace equation, which you covered in your differential equations class. And this is the way that we're going to be using it. Second derivative of h with respect to x plus the second derivative of h with respect to y equals 0. And we're going to find that the solution is a set of orthogonal functions. And when we solve this, like I said, you've solved this maybe with slightly different variables, but when we're solving this, we want to solve for h as a function of x and y. In other words, we're going to look at our system, our geometry of it, and the goal will be that, for instance, you give me an x and a y, and I can give you an h head. H is head. Okay, you all know what head is. So our goal, and actually for doing this, we're very interested in getting the head at various points. From the head, we're going to get the pore pressure. So in practice, now when you're in practice, we solve this Laplace equation basically in two ways. One is a finite element method with you use software for it. And the other is a flow net. We're going to do the flow net. Okay, so the concept is this. I have a dam here. This dam has a cutoff wall. This is a cutoff wall here. And the purpose of building a dam is that you're making a lake. So you have a lake on one side with a high water level and a downstream and with a low water level. And when that occurs, what happens is that we cannot seal things perfectly. This never happens. What happens is that because the water level is high on this side and low on this side, the water wants to go around the dam underneath it. And that is what we're interested in. We're interested in figuring out what path the water takes to get from one end of the dam to the other. And what I've shown you here is, it almost describes itself, looks like a net. And that's what we call, that's why we call it a flow net. What we're going to do for these problems is that I'm going to give you the flow net, and then you are going to make calculations from the flow net. And here we call these lines the flow lines. That's a flow line. That's a flow line. If we followed a particle of water here, that particle of water would take this path. And then the other extreme is there's a particle of water that basically just goes along the bottom like that. So in past semesters, I've made students draw their own flow nets at times. Or I make you draw your own flow net. That usually takes place in the lab. I'll give you an assignment or something, but it's hard for me this semester to actually be able to make you draw your own flow net. So but it's actually quite straightforward. I wish I could. I'll show you how to do it. And then I'll give you some problems to do, and you can try it yourself, but in the end, I won't be grading them. You just do the best you can. It's quite straightforward, and it works. The amazing thing about it is that it's simple to do, it's fast, and it works. It's, in a lot of ways, if it's appropriate, it works much better than a computer program. So, in other words, for this particular geometry, there's my dam, and I have to make my flow net to conform to the, basically it conforms to the shape of the dam a little bit. Here's another one. Now I have a different shape of a dam, just to make things a little bit different. And again, I have a high water table and a low water table, so once I know that, then the water is going to be flowing in this direction, like that. And here is a flow line right here. Goes underneath here. Here's another flow line here. Then there's an extreme flow line at this end and an extreme flow line at this end. What does that mean? That means if I put a particle of water, or a particle of water that starts here is going to follow this path. If I follow a particle of water here, it's going to follow that path. And amazingly, it does pretty closely. Assuming the soil is uniform. Now, the other lines in the flow net are called equipotential lines or equal head lines. So in other words, these lines here are lines where the head is equal. In other words, all along this line here, if I figure out the head there and figure out the head there, it's the same. What do I mean by head? Now, we've talked about piezometers, and so what do I mean by that? If you remember what a piezometer is, it's like a manometer in the soil. We put a piece of plastic tubing in the ground at a particular point with an opening right there, for instance. So this plastic tubing would go in the ground and go up like that. And then what we would find is that the water level in that plastic tubing, for instance, would go to this level. So in other words, we could measure the water level in that plastic tubing. It might go to there. And but if I put that same plastic tubing here, then the water level, since it's an equipotential line, would go to the same level. So in other words, the water level in the plastic tubing and the piezometer would be the same. Now, to get the pore pressure at these points, the heads may be the same, but the pore pressures at those points are different. Why? Because the way that we get pore pressure, our water table pore pressure, it's what? It's the level of the water in the piezometer minus the level of the point. It's this distance here times gamma W. So this would be, for instance, H1. For the other point, that distance would be this. This would be H2. And H1 and H2 are not the same, so that H2 gamma W would be greater than H1 gamma W. So the pore pressure at this lower point would be greater than the pore pressure at the shallower point. So again, we have the same head, but not the same pore pressure. So our goal in a lot of these problems will be to get the pore pressure at different points. And the goal will be, or the method will be, to figure out the water level in the piezometer and then multiply it times, well, gamma W. All right, let's take a look at a little demonstration of this. We have one of these models in our lab, and if you notice, there's on the right side we have a high water level, on the left side we have a low water level, and there's a wall in between. And what they did in this experiment, and this is what we do in our lab, is that purple is food coloring, and the food coloring traces out the path of the water, and it makes the flow lines. So that sometimes what people do is that you can build a model and then create this, and you get the flow lines drawn for you. I'm going to show you a more mathematical and simpler method to do this. You don't need to build a model every time. It works better just to draw this out using the methodology that I'm going to show you. But that's the concept. Notice that this is not turbulent flow. This is laminar flow. If you remember, turbulent flow is what? It's topsy-turvy and the water gets mixed up and everything like that. Laminar flow is where, I'll play it one more time, is where the particles of water don't cross. Notice there's no crossing of the flow lines. They're sort of parallel to each other, and that's the way water flows through soils. It doesn't, it does not go, it doesn't cross, it's not turbulent, it's just laminar flow, just like that. And so the flow lines are, in a sense, parallel to each other. They're not exactly parallel. You can see that they get closer to each other and separate from each other. So they're not parallel, but they don't cross. That's one of the main things, is they don't cross. They can get closer, they can get farther away from each other. And it can be a dirty job, this is the, but a large part of geotechnical engineering is relegated to abstract calculations and computer. That is the concept. That's the way that it works. And if we could build a model that looks, we could build a model that looks just like this, for instance, in the lab, and we would end up with getting flow lines that look like this. Okay. All right, what I'm going to do is, let's see, okay. I'm going to show you how to draw a flow net briefly, and this is how simple this method is. So I've done these a number of times, so they're a little bit easier for me to do. But the way that you do it is you first envision a particle of water here, and I know where that one's going to go. It's going to go just like that. Okay, so there's one flow line. I envision a particle of water that's going along the bottom. Where is it going to go? There's another flow line. So you draw the flow lines first. Now the harder ones are the ones in between. And I don't know how it's going to go because I haven't looked at this problem in a long time. So I just make a guess, but I've done these before, and I'm going to say, it's probably going to come along something like that. And then I draw another one. We're only going to draw a total of 4 flow lines. And I don't know where this is going to go. Oops. I'll just say it looks like that. I don't know if this is right, but then what happens is that we now draw what are called the equipotential lines, the equal head lines, and we see whether or not this works. So my goal is to draw what we call squares. What is a square? In other words, if I've done it right, then, this is a square. I mean, it's obviously not a square, but it has some aspects of a square. We always call them squares. They're not really squares, but they have some aspects of a square. Same thing with this one. This should be a square if I've done it right. again, it's not really a square, but how do I judge it whether it has the properties of a square? Well, it's pretty straightforward in the sense that what I'm looking for is simply the width and the height in the middle of it. The width and the height in the middle of it. Those are approximately equal, then we call it a square. Well, this one's not bad, this one's not very good, so I'm going to start over again and draw my flow lines slightly differently. So, and this is the way that you have to do this, is that you, it's trial and error. So I'm going to try, I'm going to try bringing this in a little bit. And then I'm going to move this out a little bit. And again, I don't know whether that's right or not, but I experiment with it. And so now I'm going to make my square. So the first thing I have to do is make the first one a square. So in my mind, if you look at this, that's approximately a square. I can't do too much. And then now I'm going to curve this around. Because the Laplace equation is a series of orthogonal functions, what I'm looking at is right angles. I need to have approximately a right angle there, approximately a right angle there, approximately a right angle there. I'm looking for a series of right angles. They're not perfect, but approximately. That means, and down here, try to make them, I can't just helter-skelter draw these things in. So, with this particular flow net that I just did, well, this is not a very good square again. So I'm going to give it one more shot, and then I don't want to belabor this because it's on a video. And I sort of like this first flow line, so maybe I will leave that, and I'll just make the next flow line come in a little bit closer. And try that. And now something along these lines. Now this square is pretty close to being a square, and that's sort of a square, and this is not perfect here. Okay, now what do I have? Oh, this doesn't look good. So I have to bring that flow, I got to bring that out farther like that. And, well, let's see. Oops. Try this one more time. Something like that. And then maybe something like that. Oops. Still not. Anyway, it takes a few trials. I don't want to. Now I'm just going to finish it up here. The beginning is the hardest. Once I've got the beginning. Okay, something along those lines is the flow net. Now, I'll show. So it took just a few minutes, and that one wasn't that bad. If you look at each individual square, each square is a different size now. But let's see, when I spent a little more time. Oh, this is a different one. Okay. Anyway. Here is a finished flow net, and how do I know that it's not too bad? Well, again, I look at this distance compared to that distance, about the same. Then it's okay. I go to each square. That and that are about the same. I look here, that, and that about the same. And you can see that there's some tiny squares here. There's tiny squares in there. There are big squares over here. And so each square is not the same size, but we're not looking for each square being the same size. We're just looking for each square to be a square within itself. You can pause the video and try to sketch something like this. I'll send you some problems. This is not good. Okay, so this is an example of do not do this. So in other words, this is completely wrong with lines just all over the place, and they are not squares. You can see there's no square there. That's not a square. This is not a flow net. It should look more like this one here when you do it right.